one of the results of the CoRoT and Kepler revolution was that our favorite star before the launch of these two satellites are swept away, and we don't talk about this star because practically we forget them, because they are new stars now joining giving us more results in a much more quantitative way. And one of the stars who survived to this epuration was RR Lyr itself, because it was in the field of Kepler, and then it was observed by Kepler for a long time, and there are also several papers that have been published about the presence of the period doubling, as Robert told us just before me, and also the presence of other radial mode in the light curve of Kepler. And this is the result of the observation of Kepler during his life, and you can see clearly the Blazhko effect affecting the time of maximum, and then also the amplitude of time of maximum. But if RR Lyr itself is a star that can tell us a story, because it has been discovered in 1899, and the first observation was taken July 20, 1899. So there is more than 1 century of observation, and this is, for example, probably the data center of this time, who is chairing the people reducing the Henry Draper collection to memorial to extract the information about variable stars. And then, if you are a historian, you have to preserve this history. And this was my colleague Jean-François Le Borgne made here in Toulouse. He keep updated a database containing all the maxima observed, not only for RR itself, but for all the RR Lyr observed and discovered in the past century. And this database is known as the GEOS RR Lyr database. It is available as this website. And And this database was, this observation of RR Lyr was performed now also by means of automatic telescope by two CoRoT telescope, which are built to observe gamma ray, the optical counterpart of gamma ray burst, but can be devoted also to the survey of other interesting astrophysical topics. So it is devoted also to observe RR Lyr stars, and we have already published 2 papers about the evolutionary changes of period of RR Lyr star during the past century, and also on the shape of the Blazhko effect of the galactic RR Lyr stars. And so the first thing, if you have 1 century of observation of RR Lyr star, of RR Lyr itself, then calculate an ephemeris and looks how the OMC changes. And the first result we obtained is that the period of RR Lyr itself is changing continuously since it's discovered, and starting from 1845, the period continued to oscillate between a lower status, the last digit, the number here, the last digit of the observed period, and this one. And you can see there are periods of some years in which the period is very long and the period is much lower. So RR Lyr oscillated continuously between these states. The pulsational period of RR Lyr oscillated continuously between these 2 periods. And the natural question is how the Blazhko period did in the time that the pulsational period changed. So we, again, starting from all the history RR Lyr told us, we subdivided into different epochs, and we study the value of the Blazhko period, starting from the historical values at the beginning of the past century, just to now with the Kepler RV1 and the more recent CCD observational year. And what we discovered is that the period is completely decoupled. Here you can see the up and down change of the pulsational period, and the Blazhko period was stable since 1975, and then dropped to 40.8 days to about 39 days. You can see perhaps here to see that the peak on the periodogram moved from the left to the right of the red line. So the first result, the second result was that the 2 periods are completely decoupled, and they go with, in a way, and the other in the other way. So if RR Lyr star has any history, it is important also to monitor it also before the end of the observation of Kepler. And some years ago, again, Jean-François and Alain Klotz have the idea to observe RR Lyr from ground, but not with the dome you can see here, but with this small telescope, which has been timed VTT, a very tiny telescope, which is constituted by an monture and basically a CCD with a photographic tube, and with the only goal to observe RR Lyr only all the evening it was possible, all the night it is possible, to extract the time of maximum. No importance about the shape of the light curve, but also only to obtain the time of maximum, because it is the best way to obtain results without going in sophisticated observation. And this was a result. The observation started in 2008, and the amplitude of the Blazhko effect was very high. You can see that OMC can reach 600th of day, and progressively in the past year it decreased to a very low value. And we saw that Kepler observed the Blazhko effect. This was the light curve, the OMC behavior in value and amplitude as recorded by Kepler, and this is what happens if we added the VTT maxima. You can see there is a perfect superposition where the observations are simultaneous, and the extra information is about the amplitude of the OMC before the start of a Kepler observation and now. And this is what we published in a paper appeared a couple of months ago in Monthly Notice. And the news is actually that if we compare the observation taken by RR Lyr this year, the last maximum was observed past Thursday, we can see that the amplitude of the Blazhko effect of RR Lyr is practically zero. There is no Blazhko effect at all at the moment. All the observation of the maxima are scattered, which is due to, are scattered by exactly the incertitude expected in the maximum determination. So this is another kind of information we have on the Blazhko effect. The Blazhko effect can also practically disappear from the light curve of our stars. Yeah. So let's move to Cepheids, which are a sort of stars that are not very common in the satellite field of view, and the only results published till now about the Cepheids are published on the basis of Kepler observation of V1154 Sinus, which is a Cepheid that it is in the field of Kepler, and there is a paper published by Alice Derekas and the collaborators 3 years ago, and Kepler. The Cepheid was highly saturated in the Kepler field of view, but it has been corrected, and some interesting results are obtained. And the main result was indeed that there is a sort of period jitter of the star arriving to 0.015, 0.2 days, and this period jitter observed over a temporary baseline of 120 cycles was not expected in the literature, in the theoretical model, sorry, and indeed it was promptly an explanation has been proposed. So there are something spots on the surface of the star changing the light curve occasionally, and then this can provoke the change of the OMC. You can see here the simulation made by Heidi Nelson and Richard Ignace, and you can see that there are some variations that are very small. It is just 1,000th of magnitude. It is not so much, but it is able to produce some OMC scatter. And in a certain the news about the news we have is that actually we discovered also Cepheids in the CoRoT field, and they are at least 4 at the moment. 3 were observed in short run, and 1 in too long run, because the field has been repointed several years later. And we have 2 fundamental mode pulsators, this one, and 2 overtone, first overtone pulsator. And the analysis of this star at the moment, well, they confirm the nature of the star. Here we can see it plotting the Fourier parameters in function of the period. You can see here the progression due to the Hertzsprung progression, the progressive change of the light curve of Cepheid with the period. It is 10 days, more or less, at the right hand of the plot. And you can see these are the fundamental pulsator in green, and it is the first overtone pulsator with probably a resonance here producing a discontinuity. So we have two CoRoT Cepheids as first overtone and two CoRoT Cepheids are fundamental mode pulsator. And well, I can skip this one. And which are our results about the period jitter? At the moment, it seems that the only Cepheid we can analyze it is the Cepheid we observed twice. And you can see here, this is the first long run of CoRoT. This is the second, which is a bit shorter. And you can see that all the observed scatter for the OMC are between 3 sigma, where sigma is the square, is the standard deviation of a linear fit between the maxima, so it is 5,000 of days. And all the observations are between 3 sigma, with a full amplitude of about 100 of magnitude, so it's 100 of days. So it is not really too much. It is less than the Cepheid observed by Kepler. And, but we have some significant variation in the Fourier parameters, especially the phi2 the phase parameters involving the fundamental and the first harmonics of the light curve. Against all the revolution, there is a conservative party, and in a certain sense, the Cepheids are a conservative party of the revolution because additional modes were discovered in high amplitude delta Scuti star, additional mode has been discovered in RR Lyr, as Robert told us, but no additional mode was discovered in the Kepler Cepheid. So it seems that there are no Cepheids, that there are no additional mode in the Cepheid. To see the point, we analyzed the CoRoT observation of the Cepheid we observed twice. And the first results were very impressive because we had the impressions that we discovered as an additional mode. And this is also the reason for which the paper has not published on time, and it is been delayed. Because when reducing the first long run, we had, after removing the contribution from the main frequencies, we had some signal left here. This signal is left by the fundamental, the main pulsation itself, because there are some residuals close to them, as often happen in high amplitude pulsator. Note that the amplitude of the star is 1/10 of magnitude, and these residual peaks are of the order of 0.5 millimag. So there is several order of magnitude of difference. And when observed in the subsequent long run, the peak, this peak, that it is not related to the main pulsation, persists. And it seems that it was a good indication. It is just above the significance level. It was the indication of an additional mode excited in the light curve. However, it was not convincing to me because this mode has no combination term with the main frequencies. This happened in delta Scuti star, this happened also in RR Lyr, and it seems that it doesn't happen here. So after a while, we changed the approach, and we calculated not a global fit from all the measurement, but a fit, you calculate a residual from a single fit of the fit of single cycle to have a much more clear explanation maybe of the small jumps of the light curve observed in the exofield. And what we discovered is that actually all the signal here disappeared the spurious signal at the main frequencies, but also disappeared at this peak. So our idea is that it is a sort of spurious peak due to the time sampling and due to the fact that there are some jumps in the light curve of CoRoT. This fact is also corroborated by the fact that the six times the frequencies, the 5 harmonics of the main frequencies, persist in the power spectrum after subtracting the single 6 feet. So no signal has been subtracted by changing the procedure because the six time F give us the information that you preserve the signal. All this as a period has been something that it is spurious. So our guess it is the fact that the additional mode doesn't exist. Okay. And this effect has been observed also in the chromatic mode by CoRoT, in the exofield. So we have a light curve in green, in blue, and red. And what we discovered is that it is actually, there is some phase shift between the two colors by doing photometry color by color. This is well demonstrated by the three value on each long run. As you can see, the blue anticipates always the others that has been delayed. So there is a chromatic information that it is contained in the CoRoT data. And it is a nightmare to reduce chromatic color. It is well known because, for example, maybe you can see here it is some problem of the satellite jitter, not the star jitter. And you can see here that the blue light and the red light showed a rain. On the other hand, the red part of the light curve show an increase of the flux. The total light curve is perfect, but you have some chromatic effect that you have to remove. And there is also a minor jump here observed only in the blue, but not in the green and the red, and it persists in the blue. So you have to be careful in analyzing the data. But the results may be rewarding because actually CoRoT is the unique instrument able to produce information about pulsational mode in the space. And the exofield has this opportunity, and I guess we should not forget it, both for asteroseismic study but also for the exoplanetary field, because after several trials we have an hypothesis, a work hypothesis, not more than a working hypothesis, that planets with a small mass have also slightly achromatic transit. This is a result we published last year. So do not forget that CoRoT is giving information about the color and to produce also information about, to give us information about the mode identification of our star. I am a bit late, I guess, so I left the summary and the conclusion on the screen if you have any questions. Thank you for your attention.
Any questions, comments?
Ennio, what can be the physical reason for the disappearing of the Blazhko effect in RR Lyr?
I guess there is no good explanation for the Blazhko effect itself, so it is very hard to say what it is a period. I really don't know. What I can say is that was my personal path in the understanding of in the non-understanding of the Blazhko effect, if I would be more precise. At the beginning, I think that I thought that it is possible to explain everything with a mathematical approach, for example, adding mode, and given the complicated behavior of the Blazhko effect as the interference between the pulsation in the radial mode with several non-radial modes. But the observation tells us that it doesn't work, because the Blazhko effect is not a clock. It's not a clock, indeed. It's not a clock for what Roberto does. It is not a clock for RR Lyr. If hypothetically we observe RR Lyr for the first time this year, we see that it is not Blazhko effect at all. So I guess it is something that deserves several theoretical investigation. And I guess also the fact that the period of the Blazhko effect and the pulsational period are completely decoupled. It is a constraint that can be considered in the theoretical modeling of the Blazhko effect.
Any more questions? No? Okay, so thank you again, and thanks for all the speakers.